Hello everybody, this is the second clip of chapter 6, okay, which is about the multivariable calculus. Okay, so on this clip we are going to talk about the derivative of several variable or multivariable functions. Okay, so let us recall a little bit that if you have a single variable function y equals to f of x, okay, then the derivative at a particular point x equals to a, it is represented by a limit of f of a plus h minus f of a over h, of course provided this limit exists. Okay, and actually this one geometric representation is that if this is the point a, then this limit or the derivative is actually the slope of the tangent line to the curve y equals to f of x at the particular point x equals to a, just like that. However, if you remember last time what we introduced two variable functions, okay, or like several variable function, but we emphasize on the two variables function first, z equals to f of xy. Then instead of the curve like that, we have the surface instead. Okay, we have a surface z instead. So by having the surface, okay, how can we find the slope of one of the point on the surface? That will be pretty difficult. So what we did instead is that we are going to fix one direction. Okay, for example, if this is the z, the y, and the x axis, okay, this is z equals to f of xy surface, then we are going to fix like one direction. For example, we are going to fix the y, okay, we're going to fix the y to like one value of y. For example, y equals to b, okay, here. And then after you fix one value of y, then it's look like you cutting this surface, okay, you're cutting this surface by a plane, a straight paper, y equals to b. So after you cut the surface by the plane, then what you are going to have is the curve, okay, that is the cutting edge like this. Okay, so after you having a curve, then the problem becomes two dimension, right? Becomes this kind of curve like that. So from the curve you can find a slope of this curve. Is it a slope of this curve? And this curve, because your y is already fixed to be a particular number b, then it means that your function right now depends on the variable x alone. So it go back to a single variable function problem. Okay, so this is the idea. So let's look at what we are going to have right here. So as I told you, we are going to have a surface. Okay, here's a surface. So let's say the z equals to f of x and y, and then we are going to fix, or we cut, okay, we cut the surface by this plane. Okay, so by this straight sheet of paper. Okay, this plane is called y equals to y0. So your y is fixed. So after your y is fixed, then you have this curve right there. Okay, you have the curve right there, here. Okay, the curve, which is the cutting edge between the plane and the surface. Okay, and this curve, it is actually represented by z equals to f of x y0. This one is already fixed, okay, to be y0. So the thing that is really a variable is only the x alone. So after that, you are going to find a derivative okay, with respect to the variable x. Okay, so the derivative with respect to a variable x will represent the tangent, okay, the tangent line to that green curve, okay, to the curve z equals to f of x, y, 0. And this one we call the partial derivative, okay, the slope here, it is a partial derivative of function f, okay, with respect to, okay, we are going to abbreviate by WRT, with respect to a variable x, okay, a variable x. And to define it in terms of a limit, then we are going to use the limit like this, okay, because the only thing that is changed is your x variable. So your x will change from x plus, from x here to x plus h right here, and your y is fixed, okay, you see your y is always the y on both ends. And then you are going to find the limit of x plus hy minus f of xy, and then over a small change in h, and then that change will go smaller and smaller, okay, as your h goes to 0. This one we'll call a partial derivative of a function f with respect to a variable x. And the notation, okay, usually you remember the notation previously, you have a df by dx for a single variable, right? But to indicate that your function depends on one, more than one variable, okay, a derivative will use a curve like that, okay. So instead of a straight d, we use a d like a curve d like that, okay. So somebody may read it as a curve f by curve x, okay. However, to me, I'll read it as df by dx, okay, or a partial derivative with respect to x. All right. And another notation in terms of a single variable is that you can use f prime, because if your variable, okay, is only one variable x, okay, you can use the prime to indicate your derivative. However, if you have several more variable, instead of using a prime, you use a subscript, okay. So this one, in terms of several variable, we use this notation df by dx, or your f subscript x, or sometimes we use dx f or d1f, okay. So it depends on each of the book that we'll use, okay. However, usually we are going to use it, the subscript instead of something at the top, okay. So this one, if you talk about the dz by dx or df by dx, it is actually the rate of change of a function z or the f of xy with respect to x when your y is fixed, okay, when your y is fixed. So of course, on the other hand, if you fix your x, okay, and then you cut your surface at a fixed value of x, let's say at x0, you cut this surface by another straight sheet of paper at your x equals to 0, you got another curve, right? Okay, you got another curve just like that, okay. And this curve also have their own tangent line, okay. And the slope of this tangent line, now it is a partial derivative, okay, of a function f with respect to, now is a y, because right now the fixed value is your f. So this curve is actually represented by, okay, the curve is actually represented by f at x0y, okay, f at x0y. All right. So as we told you, okay, your x is fixed and your y is the one that changed. So it changed from y to y plus h, and you find a difference divided by a small change h, okay, as your h goes to 0. This one, it is a partial derivative of a function f with respect to a variable y, okay, with respect to a variable y. The notation is a df by dy. So same thing, you may have df by dy, dz by dy, f sub y, or sometimes you have f sub 2 as well, but usually they have df, d2f, or dyf like that, okay. That will be more common. So the dz by dy or df by dy is simply the rate of change of a z value or a f value, okay, the f value with respect to a variable y when your x, okay, the variable x is fixed. It's fixed. So what does this mean? It means that to find a partial derivative, you just need to look at it carefully, okay. To find a partial derivative, you just have to look at it carefully, that which one will be a fixed or a constant, which one will be a variable under consideration, okay. And of course, instead of a two variable, you can determine or you can define your partial derivative for a function of more than two variables as well. For example, if your function contains x1, x2, etc. to xn, then partial derivative of this function with respect to component xi, okay, the I component, it will be again a difference, okay. You find a difference of a function value at xi plus h, and of course this one, it is the xi, okay. However, the rest fixed, okay, to be the same. The rest is fixed to be the same. Only your xi that's changed, and divided by a small change h, okay, and let your h goes to 0. Then this one is a partial derivative of a function f with respect to a variable xi. So it's a rate of change of your z with respect to xi when the other variable are fixed, okay. So the procedure to find a partial derivative, for example, if you want to find f of x, you are going to treat your y as a constant, and a derivative will go directly to where the variable x is. For example, okay, this one, the one with respect to x, right? So your y is a constant, okay. Of course, the one is a constant as well. So you are going to, the y, pull it outside because it's a constant, and a derivative will go directly to where the x is. The y is outside, and a derivative go directly to x fourth, and of course derivative will go to a number 1, and all the the rule about finding derivative can be applied. For example, this one, a derivative can be separated among an addition or subtraction, all right, and a derivative can be a product rule and quotient rule and all the power rule, all the kind of rule for the derivative can be used, okay. So this one, it is a y and then 2x. This one is a y square and then 4x cubed, and then it is a 0 because of course that's really a constant, and you usually write as 2xy and 4x cubed y squared. On the other hand, if you want to find a derivative with respect to y, then your x now is a constant, okay. Of course 1 is a constant, so all the x is constant, and a derivative go directly to where the y is, okay. just like that. So this one will have x squared, and then a derivative of y with respect to y will have x fourth, a derivative of y squared, we got 2y, and then of course this one it is 0. Or you can simplify it to be x squared and 2x fourth y. So that is the derivative of this function with respect to y. Okay. So let us make sure that you can find all the partial derivative. Okay. For example, if you want to find f sub x, okay, and also let you guys familiar with all the notation as well. The f sub x is a partial derivative with respect to x. Okay, so it means that right now the only thing that is variable is your x. So your 3y is a constant, so you pull it out first, and the derivative go directly to x squared, which is a 2x. A square root of y is a constant, and a derivative go directly to x, and a derivative of x with respect to x is simply a 1. So this one can be simplified to be 6xy in square root of y. What if we want to find f sub y? So to f sub y, this one is a variable, this one is a variable. So your 3x squared is a constant, you can pull it out. Derivative go directly to y, which is 1. X is a constant. A derivative go directly to a square root of y, which is 1 over 2 square root of y. And you can simplify it a bit to have this expression, f sub x, f sub y. Okay. How about this one? This one, if you want to find a derivative with respect to x, your x here is a variable, your x there is a variable, the rest they're constant. So you pull out the 2y, a derivative of x with respect to x, you pull out the 3, again a derivative of x with respect to x. What is a 2y? It's a constant, so a derivative is 0, and 1 is also a constant, a derivative goes to 0. So it is simplified to be 2y plus 3. What if you want to find a derivative with respect to y instead? Here your y is a variable, your y there is a variable. So it means that the 2x has nothing to do, you pull it out. And a derivative go directly to 1 over y. And 1 over y is actually y raised to the power negative 1. So you have negative 1, y raised to the power negative 2. And then now all the x are constant, so you have 0. The 2 is a constant, derivative go to y, which is 1. And the 1 is a constant, a derivative goes to 0 as well. So you have negative 2x over y squared plus 2 as your final answer. Okay. Now, if you talk about a 3 variable functions, okay, a 3 variable function. So this one, you can simplify f sub x. So of course, the rest, only the x, there's a variable. So your 3 over y squared plus z squared, not z squared, z cubed, they are all constant, and a derivative go directly to x, which is 1. How about f sub y? The 3x is a constant, your y here is a variable. So it's actually, you are going to find a derivative of what? Let's see, it can be written as f of x y z equals to 3x y squared z cubed raised to the power negative 1, right? So to find f sub y, the 3x has nothing to do, and this one you use a chain rule to have negative 1, y squared plus z cubed raised to power negative 2, and then a derivative of the inside with respect to y, so you have 2y, but then this z is a constant, so you got 0. Or you can simply do a multiplication to have negative 6xy over y squared z cubed raised to power 2. Okay. Then, I mean, if you want the f sub z, you can use this expression again because your z is at the bottom. So the 3x has nothing to do. Now the chain rule will give you negative 1 here, y squared z cubed raised to power negative 2, but then a derivative of the inside with respect to z, you have a 0 here, and then your z is a variable, so you have a 3x z squared, and you can simply calculate it as 9x z squared with a negative value, and y squared plus z cubed squared. Okay, so that will be your derivative with respect to z. Okay, of course, I mean, what is a application on a derivative of a single variable that you can think of? The first thing, if you are given a cost function, okay, cx, then you can find c prime x as a what? A marginal cost, right? And then you have its own interpretation, remember? Okay, so it's like a increment of a cost if you produce like one more unit from the original x, remember? So this one, we have the same thing, but you elevate yourself to a cost of, you know, two variable. So here you have a marginal with respect to x, a marginal with respect to y, and that got its own interpretation. Okay, they got their own interpretation. All right, and also, of course, I mean, not only the cost function that you can find the marginal cost, right? Actually, a revenue, a profit. Okay, you can find all the marginal as, I mean, of any other function as you like. Okay, so we are going to stop this clip at this point first. Okay, and for the next clip we are going to talk about the application, but it's only a simple application, okay, of the derivative, okay, especially of a partial derivative of, you know, at least two variable functions, okay, which is applied on the business aspect. Okay, so we'll see you on the next clip. Bye bye.